Okay, let's continue. Because I had two more cases I want to show you. And the next case is called a graph surface. And let's see how this comes about. Ingredients. First of all, we have a height function. Let's call that h of x comma y. This is a height. And then you're given a field call it E in the x, y plane. And this field here is, so to speak, elevated onto the graph surface. Let me show you what this means. Now we are in 3D, x, y, set here, and we have some kind of a set in the xy plane, and this is my field E. And then I have some kind of surface. In 3D, it may look like this. So what you do then is that for a specific point, that is x comma y, comma 0, that is the point in the xy plane, you go vertically up to the surface, say it is this point. And you do this for all the points of E, that is, so to speak, you elevate so this is the elevated surface. And how does that look in an example? In a specific example, I take the height function as x squared minus y plus 1. And then I take my field in the xy plane as a rectangular field limited for x from 0 to 3/2, and in the y direction from 0 to 1. So this is my field, and it will look like this. You have then that this is 3/2, and this is 1. So when you then take your parameter representation, then you can just use x and y as parameters, because you have this rectangular field. So if you choose x to be u and y to be v, then you still need the third parameter. But the third parameter is simply the height above the xy plane. So this is your h function here. So you put in x squared minus y plus 1, but you use the parameters that you have just introduced. So you get u squared minus v plus 1. And your parameters, they are, of course, limited in the same way as x and y. So u goes from 0 to 3/2, and v goes from 0 to 1. Let's look at the same problem, but a bit different example. We take the same height function x squared minus y plus 1, and E is now triangular shaped and with vertices, let me see, get this right, 0, 1, 1, 1, and 1, 0. So how does this field now look? Yeah, you should just plug in the vertices 0.1 and then 1.1 and then finally 1.0. So these are the three vertices. So this one here is your E. Now it's no longer axis parallel, an axis parallel rectangle, but this is how it works. You have to map this or have a map from a rectangular area with parameters onto that point. And the idea here is, here in 2 dimensions, let's take x as a parameter. We call that u. And then you look at this line here, from this point to this point. This line here is called, the equation for that line is y is equal to 1 minus x. The slope is minus 1, and it goes through 1 here. So whenever you are going to parameterize such a line segment here, you need the starting point and you need the end point. So the starting point here is u, that is the first coordinate, comma 1 minus u. And this is because this point is on this line here. So whenever x is u, y is 1 minus u. This point here is u, that's the first coordinate. The second coordinate is 1. So when you have these 2 points, then it's easy to say or it's easy to make a parametric representation for this line here, because you take the initial point, that is u, 1 minus u, and then you take the second parameter times this vector here. And this vector here you get by taking the end point and subtract the first point, or the initial point. So if you're looking at the first coordinates, you have a first coordinate u here, and you subtract, you get a 0. The second coordinate is 1 here, and then you subtract 1 minus u, let me write it, 1 minus u, and you get, if I write it together here, I get v times 0 plus u, that is u, and here I get 1 minus u, that is this first coordinate, and here I get 1 minus 1, that is 0, and then minus u, that is u, so I get plus uv. And again, u should belong to these intervals. U is running from 0 to 1, and v is running also from 0 to 1. Now you have described your x and y's, and since it is this elevated surface here, and you have your height function, then it's easy to write down the full. Now I call it 2 to distinguish it from this one, because now it's in 3D. And this will be the parametric representation for your surface and your graph surface. And the first coordinate is u, and the second coordinate is 1 minus u plus v times u, or u times v. This is these two coordinates. And then for the third coordinate, I just plug the two first coordinates into my expression for the height function. So I get x squared, that is u squared, and then I get minus y, I have it here, and then I get plus 1. And again, u is in the interval from 0 to 1, and v is also in the interval. So this is a parametric representation for your function. And again, I refer the figure to the Maple demo, and you can look at that. But when you have this one, you can easily compute the Jacobi function. Just differentiate this with respect to u, and then with respect to v, and take the cross product of these two tangent vectors, and then take the length of this cross product, and you have the Jacobi function. Now, the final type of surfaces that you should know is a surface of revolution. And here we have, again, I list down the ingredients. The first ingredient is what we call a profile curve. Okay, and in our presentation, we have this profile curve in the x set plane. And then we have an angle with which we rotate K, that is our profile curve, about or around the z-axis. This is how this is formed. Let me just sketch what this means. Let's say we have our x here and our z here. And let's say we have a curve like this. So this is my curve K, and then I take this curve here and I rotate it around the z-axis, or in fact, I do it the other way around. That should be the correct thing. And what you get out of it is you get this surface of revolution. Let me see if I can draw this like this. So it is rotated around So imagine you have some kind of bowl or vase or what have you. The thing is now that K should be given by a parametric representation. K is given by a parametric representation like this. You have the x coordinate called g of u. Now, since K is in the xz plane, the second coordinate is 0, and then you have the third coordinate as x of u. This will describe, say, an arbitrary curve in the xz plane, and now we shall see what we do when we rotate this. Let's look at it. Now this was the xz plane. Now I go at the top of the z-axis and I look down on the xy plane. So imagine you have your vertically above the plane of the blackboard, you have your curve between these points here. This is your profile curve. It's up here in space. And then you rotate it. Say you have rotated it some angle v. So on this axis here, your profile curve is now between these 2 points here, but we haven't changed the profile curve. So if you're looking at, if you call this x1, and you call this perpendicular axis for y1, Then in the x1 z coordinate system, you have exactly the same parametric representation for your profile curve as you did in the xz plane, because this is the idea about rotating this. But then let's say that your parametric representation is given in these new coordinates. What you want to find is these new coordinates in the old coordinate system, that is in the xy coordinate system. And you can do that because you've done that a number of times. That is, you have to, say, take a unit vector here and a unit vector here. And then you have to, and if you're looking at the x1, y1, z coordinate system, then the third vector will be 0, 0, 1. It's pointing out in space. So if you choose this coordinate system, and it is rotated the angle v, then you can write down the relation between the new coordinates and the old coordinates. You have to use a change of base matrix that is formed from Q1, Q2, and Q3. And this is again easy. It's a unit vector and it's forming the angle v with the x-axis, so that will be cosine v sine v 0. Q1 is perpendicular to, or Q2 is perpendicular to Q1, so that's minus sine v cosine v 0. And then the final vector is 0, 0, 1. So now I write down this parametric representation. I have my change of base matrix here, cosine v sine v 0 minus sine v cosine v 0, 0, 0, 1. And then I have my parametric curve, and it looks like this in the x1, y1, z coordinates. It looks like this one. So that will be g of u, 0, h of u. And then it's just a matter of multiplying this together. You see you get the first row dotted with this one, and 0 times this is 0, 0 times this one is 0. So you end up with g of u times cosine v as the first coordinate. For the second coordinate, you get g of u times sine and for the third coordinate, you just get h of u. And then one could imagine that you have been so clever that you have actually, your u here is in some interval. U is from A to B. And similarly, your angle here, it could be, if you have rotated your profile curve all the way around the z-axis, you would have that v belongs to 0, 2 pi, but you could rotate it somewhat less. what I will do now is when I stop this lecture, I will upload this Maple demo to this to the CampusNet, download it and look at it. There's these 4 examples I have been through, and then there's 2 examples more. And you can look at the graphs for these parametric representations, and then you can look at how the Jacobi function is computed and how you compute integrals with that. But there's also the Maple demo up today, and use it and have fun with the exercises. Thank you.